Hello, this is Joseph Domingo, and here we have the language of mathematics. For this part, we are going to be talking about the mathematical reasoning. So, we need to first talk about the difference between inference and fallacies. So, an inference is a valid argument, and a fallacy is an invalid argument. In order for us to know if an argument is valid or not, we will need to look into the rules of each element. But before we dive deeper on what these differences are, we need to first look at an important element or symbol, which is this symbol. This means therefore. We're going to be looking into a lot of sentences and we're going to be substituting them with P, Q, and sometimes R, which would mean that there will also be sentences that has therefore on it, which will mean we will be using this. Next, we have the rules of inference. These are the formulas we're going to be using to find out if an argument is valid or not. The way we're going to be finding out what rule we are going to be using is dependent on what the argument is. So here we have the addition, which is using this formula, simplification using this, conjunction using this formula, modus ponens, or also known as mode of affirming, using this formula, and we also have modus tollens, or also known as mode of denying, using this formula. We also have hypothetical syllogism, which is using this formula, and disjunctive syllogism, which is using this formula. Let's now talk about some examples. George is a chef, therefore, George is either a self-taught chef or someone who studied in a culinary school. Now, this sentence is using the connective or, which means addition. George is a chef is our P, and someone who studied in a culinary school is our Q. Looking into this formula, we can see that how this is structured is the same as in the sentence. So, George is a chef, which is why P is on top of here. Therefore, which is why there's the three dots, therefore, George is either a self-taught chef or someone who studied in a culinary school. This follows the addition rule of inference, therefore the argument is valid. Next, let's have another example. Carl is a basketball player and a professional coach. Therefore, Carl is a basketball player. It uses a connective and, which means simplification. So we're going to be using this formula right here. Our P is Carl is a basketball player, and our Q is a professional coach. Looking into this formula on how it's structured, Carl is a basketball player and a professional coach. Therefore, Carl is a basketball player. This follows a simplification rule of inference, therefore the argument is valid. Next, let's have another example. Mark is a nice person, Mark donates to charity, therefore Mark is a nice person and Mark donates to charity. Note on how the sentence is structured. Notice how before the word therefore, there are two sentences instead of one. This means for our formula, we are going to separate them by two. So with this, let's now substitute. P is Mark is a nice person, and Q is Mark donates to charity. Looking to our formula, Mark is a nice person, Mark donates to charity, therefore, Mark is a nice person and donates to charity. This follows the conjunction rule of inference, therefore, the argument is valid. Let's have another example. If it is raining, then the school is suspended. It is raining, therefore, the school is suspended. Now it uses the connective if, which means implying, which will mean we're going to be using this formula. Our P is it is raining, and our Q is the school is suspended. If it is raining, then the school is suspended. It is raining, so the school, or therefore, the school is suspended. This follows the modus ponens rule of inference, therefore the argument is valid. Let's have another example. If it is hot, the electric fan will be opened. The electric fan is not open, therefore it is not hot. Our P is it is hot, and our Q is the electric fan will be opened. Looking into this formula, if it is hot, the electric fan will be open. The electric fan is not open. Note on the negation symbol. Therefore, it is not hot. This follows the modus tollens rule of inference, therefore the argument is valid. Let's have another example. If I study, then I will be awake for the entire night. If I will be awake for the entire night, then I will be tired. Therefore, if I studied, then I will be tired. Our P is I studied. Our Q is I will be awake for the entire night. And here we have our R, which will be I will be tired. Notice in here, in this formula, we are using P, Q, and R. If I studied, then I will be awake for the entire night. If I will be awake for the entire night, then I will be tired. Therefore, if I studied, then I will be tired. This follows the hypothetical syllogism of rule of inference, therefore the argument is valid. Next, let's have another example. The pencil is not made from expensive materials. The pencil is made from expensive materials or made from cheap materials. Therefore, the pencil is made from cheap materials. Our P is the pencil is made from expensive materials, and our Q is made from cheap materials. Looking in here, we have a not P, which is why it says the pencil is not made from expensive materials. The pencil is made from expensive materials or made from cheap materials. Therefore, the pencil is made from cheap materials. This follows the disjunctive syllogism rule of inference, and therefore the argument is valid. Next, we have the fallacies. Remember, a fallacy is an invalid argument. Just like the rules of inference, we are going to be finding out if an argument is invalid by following the formulas listed here. First, we have the fallacy of affirming a conclusion, which is denoted by this formula. We have the fallacy of denying the hypothesis, which is denoted by this formula. And we also have begging the question, which is where when one or more steps are based on the truth of the statement being proved. Let's talk about some examples. If you open the air conditioner, then you will be cold. You are cold, therefore you open the air conditioner. Our P is open the air conditioner, and our Q is you will be cold. Following this formula, if you open the air conditioner, then you will be cold. You are cold, therefore you open the air conditioner. Now, this is a fallacy of affirming a conclusion because it is possible to be cold without opening the air conditioner. Therefore, this argument is invalid. A fix for this will be using the modus ponens formula. You will need to follow how that formula is structured and rearrange the sentence accordingly. The fix for this example is modus ponens because it is the most similar to this fallacy. Let's have another example. If you open the air conditioner, then you will be cold. You are not cold, therefore you did not open the air conditioner. Our P is open the air conditioner, and our Q is you will be cold. Following this formula, we will have a fallacy of affirming the hypothesis. Therefore, this argument is invalid. A fix for this is using the modus tollens formula. Next, we have the methods of proving theorems. This is where we are trying to prove something, usually an implication. Let's first start with the trivial proof. If we know Q is true, then P implies Q is true, regardless of the truth value of P. An example of this is let P of n be if a and b are positive integers with a is greater than or equal to b, then a raised to n is greater than b raised to n. Show that P of 0 is true. Since any positive integer raised to the 0 is 1, a raised to 0 is greater than b raised to 0 is equivalent to 1 is greater than or equal to 1, which is true. Hence, the whole implication, P of 0 is true by trivial proof. Next, we have the vacuous proof. If P is a conjunction of other hypotheses and we know one or more is false, then P is false and P implies Q is vacuously true. Let's have an example. Using the vacuous proof, show that P of 0 is true, where P of n is if n is greater than 1, then n squared is greater than n. Since P of 0 is greater than 1 is false, the whole implication P of 0 is true by vacuous proof. Next, we have the direct proof. In here, we show proof that the implication P implies Q is true by showing that Q must be true if P is true. Let's give an example. Give a direct proof of the statement if n is odd, then n squared is odd. Step 1 is to assume that n is odd, and step 2 is to show that n squared is also odd. So you will need to solve. And upon solving, you will see that n squared is odd because it is 2 times a number plus 1. Therefore, the theorem is proved using direct proof. Next, we have the indirect proof. In here, we show proof that the implication of P implies Q is true by showing that Q must be false if P is false. In this example, we are going to be using the modus tollens formula. Given indirect proof of the statement, if 3n plus 2 is odd, then n is odd. Our P is 3n plus 2 is odd, and our Q is n is odd. Step 1 is to assume that n is even, which is the negation of Q. It will become n equals 2k. Step 2 is to show that 3n plus 2 is even, which is negation of P. In this, after solving, we will have our final answer. This shows that 3n plus 2 is even because it is 2 times a number. Therefore, the theorem is proved using indirect proof. And that's it. Thank you for listening.